IBM just made a public commitment that most people in tech have not registered yet. The company stated that 2026 will mark the first time a quantum computer outperforms a classical computer at a meaningful real-world task. Not a benchmark designed to make quantum look good, not a lab demonstration, a genuine computational problem solved better by quantum hardware than by anything built on classical silicon. They are calling it quantum advantage, and they have staked their entire roadmap on delivering it before the end of this year. This matters because for decades, quantum computing has lived in a cycle of promising announcements followed by quiet non-delivery. The timeline kept slipping. The problems kept being harder than expected. Even serious researchers started hedging their language around when practical quantum would actually arrive. What is different in the 2026 is that the hardware is catching up to the theory at multiple companies simultaneously, and three specific breakthroughs from the last 90 days illustrate exactly how fast that is happening. The first came from D-Wave in January 2026. They demonstrated something the industry has been trying to solve for years: scalable on-chip cryogenic control of gate model qubits. Here is why that matters. Every time you add more qubits to a quantum system, you need more control lines, more cooling infrastructure, more physical space. The complexity scales exponentially with the number of qubits, which has been one of the core reasons quantum computers have been so difficult to build at commercially useful sizes. D-Wave solved this by integrating control logic directly onto cryogenic chips, using superconducting bump bonding and multiplex converters that allow tens of thousands of qubits to be controlled with just 200 bias wires. The company's chief development officer described it as the equivalent of going from room-sized mainframes to laptops. That comparison is not hype. It is an accurate description of what scalability means for a technology's trajectory. The second breakthrough is Microsoft's Majorana one chip, announced in February 2025 and advancing rapidly through 2026. Microsoft has spent nearly 2 decades pursuing a fundamentally different approach to qubits, one based on topological superconductors rather than the standard superconducting circuits most other companies use. The core advantage: topological qubits store information in a way that is inherently more resistant to noise and errors, which is the primary reason quantum computers fail at scale. The Majorana one currently holds 8 qubits, but Microsoft designed it to scale to 1 million on a single chip. Their first operational deployment of a machine using logical qubits is expected by late 2026. The scientific community has been watching this approach with a mix of excitement and skepticism because the exotic particles Microsoft is working with, called Majorana zero modes, had only existed in theory until recently. The fact that they can now be created and controlled on demand represents a genuine frontier being crossed. The third involves IBM's own hardware progress. IBM's Heron R2 processor hit 156 qubits last year, and workloads that previously took 122 hours now run in 2.4 hours on the latest systems. To pursue verified quantum advantage with credibility rather than just announcement, IBM launched an open, community-led validation tracker alongside research partners including the Flatiron Institute and Blue Qubit. The idea is to make the claim checkable in public before it is made, not after. That is a significant shift in how quantum milestones are being communicated, and it is designed to address the credibility problem that has plagued the field. Now, here is where quantum and artificial intelligence converge, and why this story is relevant to anyone following AI. The problems where quantum computing first delivers genuine advantage are optimization problems, molecular simulations, material science, financial modeling, the exact categories where classical artificial intelligence currently hits hard computational limits. IBM's researchers are already working on quantum-assisted AI optimizers, systems that use quantum mechanics to explore solution spaces that classical algorithms simply cannot navigate efficiently. The quantum computing market for machine learning applications alone is projected to contribute $150 billion to the broader quantum economy. What is important to understand is that this will not happen in one dramatic moment. It will happen exactly the way artificial intelligence happened. first in research labs, then in enterprise tools accessible only to the largest organizations, then progressively cheaper and more accessible until it becomes standard infrastructure. The people who understood what large language models were before 2022 had a meaningful head start on everyone who waited until ChatGPT made it unavoidable. Quantum is now on that same curve. The window between the first credible demonstrations and mainstream awareness is open right now, and it will not stay open indefinitely. IBM is targeting fault-tolerant quantum computing by 2029. Microsoft's first fully logical qubit deployment is expected by late 2026. D-Wave plans to bring an initial gate model system to market this year. These are not vague research commitments, they are product roadmaps with named hardware and named timelines. Whether every deadline holds is a separate question. Quantum hardware is genuinely difficult. Some of these milestones will slip, but the direction is not in serious dispute anymore, and that is what 2026 represents. The year the debate shifted from whether to when. If this changed how you're thinking about what comes after artificial intelligence, subscribe and leave a comment. Do you think quantum advantage arrives on IBM's timeline this year, or does the field still have more surprises to work through? I want to know where you stand.